Hi, so today we'll start with the second experiment, that is waveform generation and MATLAB GUI. We'll start with part 1, subpart A, continuous signal. Unit step. By definition, we know that for unit step, the value of y is equal to 0 for all x less than 0 and the value of y is equal to 1 for all x greater than equal to 1. This is what we have done. Since x has a total of 3001 element, this command will make the first 1500 elements as 0 and the next all will become 1. Then we go to sine function. Sine of x is an inbuilt function in MATLAB. All you have to do is give it an input x. Then we go to signum function. By definition, we know that the value of y for all negative x is minus 1. At x equal to 0, the value of y becomes 0. And for all x greater than 0, the value of y is 1. This is what we have done. Once and the negative sign before ones gives us minus 1. And here we give the normal y equal to 1 for half of the axis, positive half. Next we go to rectangular pulse. Rectangular pulse of x is an inbuilt MATLAB function. All you have to do is give it an input x. These are our curves. As you can see, unit step, sine wave, signum and rectangular pulse. By default, rectangular pulse has a height of 1. Let's go to the next tab. Impulse function. We know that the strength of impulse function at x is equal to 0 is 1 and everywhere else it's equal to 0. So this is what we have done. This is our entire domain of x. We have made the centermost value of x give a value of 1 for y. What I'm saying is, since there are total 1001 elements, we have made x is equal to 0 as 1. Then we go to ramp function. What max of 0 comma x gives us is the maximum value between 0 and x. This is our x from minus 5 to 5. When we plot this, what we get is 0 for all negative x and y equal to x for all positive x. Real valued exponential increasing and decreasing. E raised to x is an increasing exponential function. E raised to minus x is a decreasing exponential function. Then we go to causal exponential. By definition, we know that for causal exponential, for all negative values of x, the value of y is 0. Whereas for all positive values of x, we get the proper graph. That's what you have done. In this bracket, x greater than equal to 0, we have made a condition that y is equal to this complete expression only for the positive part of x. So these are our curves, as you can see. See, impulse becomes 1, the strength becomes 1, okay, not the value of y, at exactly x equal to 0. This is a ramp function, real valued exponential and causal exponential. As you can see, for all negative values of x, the value of y is 0 in causal. Next we go to my favorite part, that is complex exponential. We know that complex exponential by Euler's form, e raised to ix can be divided into cos x plus iota sin x. So I've plotted it in 3D using plot 3, and then I've made the, what we can say is an image of the real part and the imaginary part on the real axis and the imaginary axis. This is a helix and these are the images. The yellow part gives us the imaginary part image from the helix and the red part gives us the real part's image from the helix. We go to the discrete signals. It's the same signals and the same codes. All we are doing is replacing plot by stem and making certain changes where required. Now there's one change in signal function. As you can see that we have made the centermost element as 0. That's by definition as 0. So this is a unit step. This is our sine wave. This is our signum. This is a rectangular pulse. Let's see. So here you can see clearly all of these have a sampling period of 1. Then we go to impulse. Since we have 11 elements, we've made the centermost element for x is equal to 0 as 1. Then we have ramp function, real valued increasing and decreasing, causal exponential. Let's see the graph. See, exactly x equal to 0. The value of y is 1. Instead of strength, over here the value of y is actually 1. In causal exponential, had we taken another sampling period, we would have gotten a more clearer image. So these are our plots. And this is a complex exponential again. Here I've used stem 3 instead of plot 3. This red part can clearly show you how the helix it's getting projected on the real axis. Next, we'll be going to some periodic signals. The first is sawtooth in continuous and discrete form. After installing signal processing library, sawtooth is an inbuilt function in MATLAB again. Since by default it has a period of 2 pi and I wanted a period of 3, what I did is multiply by 2 pi and divide by 3. Then we go to pulse. This is my code. Pulse can be anything, a Gaussian pulse, a rectangular pulse. By providing it a width of 1, since I've given here, and by providing it a period of 5, I've created my pulse graph. Then I'm going to square waveform. SQUAR of x is also an inbuilt function in MATLAB after the new library, and it also has a default period of 2 pi. So I'm multiplying it by 2 pi and dividing it by 3 to give it a period of 3. Then we go to triangular waveform. Triangular waveform is just where I have converted a sawtooth centered at the point where it's becoming maximum. That is, instead of an inclined triangle, it has become a proper triangle. Then we go to sinusoidal waveform. And these are our curves. We'll run this. It's running. See over here in triangular, I've written the same code for sawtooth as it's the same function, except I've made it centered about the point where it's reaching the maximum value. These are our plots, as you can see. Continuous sawtooth, discrete sawtooth, periodic pulse waveform having a period of 5 as mentioned and a width of 1. Then this is a normal square wave, and this is a triangular sinusoidal final. Next, we go to the C part of part 1, that is addition of signals. I have created two sine waves, and the amplitudes were given as 1, 0.75 and 0.5 respectively, and the frequencies were given as 100 Hz, 250 Hz and 500 Hz. You know that sine of omega t, where omega is equal to 2 pi into f. That is what I've written, and I directly added them with a plus sign in between. After plotting them, this is the curve that we get by addition of 3 sinusoidal waveforms of different frequencies. Now we go to the D part of part 1, that is signal multiplication. Just like the addition part, except here I wanted to separately show you what the two signals that we have that we are multiplying in the end. This is my first signal. I'm giving it a sampling frequency of 10,000, and so the number of samples per second would be 1 upon 10,000. The signal would stop at 0.5 seconds, and that is the time range that I have given. X is equal to sine of 2 pi ft will plot our sinusoidal waveform 1, and similarly this is our signal 2. Then I have created z is equal to x dot star pi, that is multiplication of the two signals, and I have plotted it. So this is our output. As you can see in red, we have a first signal with frequency f1, and this is a second signal with frequency f2. This is the multiplication of the two signals of different frequencies. Now we go to the interesting part, that is making a MATLAB GUI. If we write GUIDE in command window, this is what opens. Here we can select a blank GUI by default, which is by default, and by old traditional methods, here we have different options. Like if you want to add a push button, all you have to do is slide it. If you want to have a toggle button, all you have to do is slide it. Except, as you can read over here, use App Designer. App Designer is basically a more sophisticated way of making the GUI. So that is what I've used. This is the GUI I've created using App Designer. If I run it, this window pops up. So as it says, this is a continuous and discrete signals that we've already plotted in the previous subparts. This option allows us to select a particular graph from all these examples. Let's suppose I select rectangular pulse and click. This is my output. If I select some other, let's suppose impulse, this is the output. These are basically this push button in our component library and the drop down menu in a component library. All you have to do is for the push button, you have to call back, and over here you can see that I've created an if else block that if the user input is unit step, then what it has to open is a figure window that I've already saved from our previous subparts of unit step, impulse, etc. and so on. That's it for a second experiment. Thank you.